that's an aerobic process. It goes on in most soils unless they're super acid. There's another process that's called denitrification, okay, and that starts with nitrate, this NO3 ion here, and that's a reduction, a dissimilarity reduction of more oxidized forms, and N2O is the next to last product in that chain. This occurs under anaerobic conditions. And what's happening there is bacteria that are normally using organic matter as their energy source, so heterotrophs, and they're normally using oxygen for their respiration. If oxygen is not available, they can use nitrate or nitrite or NO or N2O, depending on where they are and what's around, as the electron acceptor in their respiration. Okay? And then if it becomes oxygenated, they turn back off, start using oxygen, and that process stops. If you have a system that is fully anaerobic and it persists for a long time, then eventually, and it was restricted diffusion of gases, you get almost all the product out as N2 gas, okay, and that's not a greenhouse gas, that's just nitrogen, like 80% of the atmosphere. But most soils, you either get diffusion out of the soil before, and there's usually these other electron acceptors, if there's still some of those in the system, are more attractive than N2O, can be used as an electron acceptor, but is sort of the last choice, if you will. Or also, soils that are sort of anaerobic but not fully anaerobic, that you can get a substantial amount of it. Usually these, well, all three of these, but these are the dominant processes that usually make it out of the soil. They're the dominant species. So N2O comes both through this aerobic and anaerobic process. One of the things, as you can imagine, with this, so how are soils going to get anaerobic? They're going to typically get anaerobic when they get flooded, right? Because you're going to slow down the diffusion of oxygen from the atmosphere through the soil pores. Certainly, intense microbial activity of heterotrophs will also lower the oxygen content, but you don't really get anaerobic soils until they get flooded. If they get flooded, you have a lot of nitrate around, then you can get big responses, very transient. This is like following an irrigation. So N2O flux is relatively small. Boom, very quickly you get a big emission because those microbes are actively taking that nitrate, denitrifying it, but then they run out of nitrate, and so, or they run out of easily metabolizable carbon or something like this. But anyway, just to suffice it to say that N2O is very transient in time and spatially variable, so it's quite a difficult process to model well. And as one consequence, so people also have done more simplified models and say, okay, we've got both anaerobic and aerobic processes going on. Nitrous oxide is being lost in both of these processes. How about if we just view the system as, these things are going on, and nitrogen is getting sort of pushed through that pipe, okay, this process. And the pipes have leaks in them, and so I'm going to make a simple model and say that, the more nitrogen I push through these processes, the more leaks out, essentially. And this is kind of the leaky pipe model. So it's just kind of a way of looking at it. And it turns out that at a very gross level, I should probably go back to that. At a very gross level, that type of a model, can be useful. And here's an example, I guess, to some extent you might say that's the theoretical justification for a model like is used in the IPCC see inventory process where if you analyze how N2O rates change as a function of adding more and more nitrogen to a system, then you can get a gross approximation of it, somewhere about 1% of that added nitrogen that you push through the system, irrespective if it's for fertilizer, or for in fixation from legumes, or whatever ends up coming out as N2O. And this other figure kind of showed, showed that, okay, not worrying too much about sort of the actual model formulation, but just saying, yes, because nitrogen is going through these processes, as we add more nitrogen, either as synthetic fertilizers or manures or crop residues or whatever, as we get more nitrogen going through the system, we're going to get more losses.
Is there any natural process that converts N2O back to a non-greenhouse gas?
There's natural processes in the atmosphere.
Does it get sequestered at all naturally, like the way that carbon dioxide does?
Well, the answer is, kind of the direct answer is sort of no, not practically. Again, it could be, nitrous oxide, if you took nitrous oxide and put it in an anaerobic environment with bacteria around, it could be further denitrified to N2. So from that standpoint, but if it's already out of the atmosphere at such low concentrations that there's going to be very minimal, there's not typically going to be net diffusion of N2 from the atmosphere into the soil in order to be denitrified.
Wait, so you're saying that so even crop residues are creating 1% of
crop residues that are essentially the nitrogen in the crop residues, because it's being mineralized from organic forms into ammonia, and it's being.
So would you have had, just as a thought experiment, would you have had global warming eventually, even if humans are not around, based solely on plant decomposition?
Well, put it this way: there has always been N2 being emitted from terrestrial ecosystems. Okay, and currently about half of total N2 emissions are coming from natural ecosystems. Okay, now some of those natural ecosystems are being perturbed by humans from long-range nitrogen deposition and stuff like that. But the answer to the question is definitely there has always been N2O being emitted. It's been a component of the atmosphere. But the difference is there are, so N2O has a fairly long lifetime in the atmosphere. One of the reasons it has this big global warming potential, but basically it interacts with ozone and hydroxyl radicals. There's a whole atmospheric chemistry. So eventually N2O can be broken down into N2.
The other atmospheric chemistry.
Yeah, and so basically then the reason you probably didn't have big fluctuations in N2O. You basically had an equilibrium, a certain amount of N2O being added annually to the atmosphere by these processes in native ecosystems with whatever the natural nitrogen cycle was, but that rate was basically being equal to the rate at which N2O is being destroyed in the atmosphere, so you have an equilibrium concentration. And that's probably, into other things, for sure there's been changes in climate and things like that that have, natural ecosystems that have changed greenhouse gas concentrations in the past. CO2 has gone up and down, although it's always, in the last million or so years, it's between 200 and 300 ppm, and it's kind of stayed there in a fairly constrained cycle. And now, we've jumped out of that cycle. Methane is another one that is, has some natural fluctuations too. I think it was about that. Yeah, I think I'll skip over that. So the objective, hopefully, if we can get this to work the next 2 weeks, you guys will also be using the DayCent model to predict N2O emissions. And this is a highly stylized one, but basically it's just pointing out that it's incorporated into the simulation model, okay? It's going to be driven by the hydrology, by the amount of nitrogen that you're adding in fertilizers, and, you know, some of that mineral nitrogen, depending on the situation, can be incorporated into soil organic matter. Some of it's being, you know, denitrified or nitrified and giving off as N2 gas. And if all works well, we can do estimates of nitrous oxide emissions using the DayCent model. If it doesn't work well, we'll fall back to this kind of IPCC methodology, and you'll do some calculations. My different systems, what are the N inputs there? And I'll use an emission factor approach to estimate N2O. I'm going to introduce one more topic before we quit here. So notice up here I got something called direct N2O and something called indirect N2O emissions. And this doesn't have actually anything to do with like direct and indirect land use change, which is another issue that we often deal with in these life cycles. What this refers to is if I'm calculating the nitrous oxide, let's say I've got an agricultural field, I'm putting manure or fertilizer on something like that, and then at that location, I'm getting some of that nitrogen coming back out as N2O. But there's other processes and other loss processes, so some of this stuff can also be volatilized as ammonia gas, or it can be leached nitrate that then goes down into the groundwater and comes up somewhere else. And likewise, that volatilized ammonia can go up, but eventually it gets deposited in some other ecosystem. So that's the idea of this indirect N2O, is as a consequence of other losses from the site of application where your direct is occurring, you can be stimulating nitrous oxide production somewhere else. And so there are also, and the DayCent model, because it looks at, you know, like a field scale, so it doesn't do a whole, you know, it doesn't explicitly do the indirect. But what it does do is it calculates, you know, leached nitrate. And so you can take the leached nitrate and calculate part of this indirect N2O. It doesn't yet, actually doesn't really do ammonia volatilization either. Just finally, I guess a couple things, yeah. So, okay, so, you know, we talked a little bit about how if you're going to build soil organic matter, you're going to increase inputs or decrease decomposition rates. It's a little bit different. So this is showing, okay, I want to reduce my N2O. What do I do? Okay, so I've got ammonium, I got nitrate. I can get N2O from either of those sources. And so what I want to do is, rather than have a bunch of this stuff sloshing around that is subject to losses, is get that into the plant as much as possible, and or do other things to, you know, reduce those fluxes. And the kind of things you can do is, you know, how you put the timing and amount of nitrogen you put on, you know, can make a difference. There are modern fertilizer formulations where you either add inhibitors that inhibit this nitrification step, or reduce the rate of say urea hydrolysis to ammonia, and do different things to try to improve kind of the timing and the plant use. And, you know, things like this International Plant Nutrient Institute talks about doing the 4R strategy, the right amount of nitrogen, the right timing, the right placement. This is kind of a little bit out, but it maybe is, you know, people are looking at N2O in agricultural systems, not necessarily biofuel, and are